Oh, it's Saturday, I get it. We're gonna be challenged. But good morning, everyone.
Good morning.
I will start off by saying this is definitely the most packed house we've had for a SECME training ever. And we're really happy to see that. Happy to see a lot of students in here. Happy the coordinators that can join us. Thank you for coming out on a Saturday morning. Especially for the adults and teachers. We know that means a lot. For those who don't know me, since I have a lot of students here, my name is Eric Leitner. I'm a science instructional specialist with the district. I am also the SECME co-coordinator for the district, along with a few others. Lisa is moving her way in and out of the room, getting some stuff out of her car. With me also is Chris Conkey over there in the jacket. We are wearing our Saturday best. This is not our normal work uniform. It might be for you, right? So yeah, we're absolutely very excited. There's a few norms I want to go over for today, just so we know. I know you'll see Lisa bringing in some treats and coffee and stuff like that. That is for our lovely presenters today. So if there are leftovers after the fact, maybe we'll let you attack it. But for now, please make sure they ate. They got here early to set up, and we want to make sure they eat something. Secondly, the camera that is pointing at me right now is going to be running the entire time of the training. So don't say anything you don't want recorded. Also, as a norm, if the presenters are speaking or if someone in the audience is asking a question, let's try to stay quiet so that the camera can pick up that audio. We have a lot of coordinators that couldn't make it, and this is their only way of getting the information, is that I post these videos for them. And I try to do the best I can. Of course, they do complain and say, we couldn't hear that one part, and I go, you should have been there. They go, the resolution isn't good. I'm like, you should have been at the event. The resolution when you were there in real life was phenomenal. But we're going to get started, so I'm going to hand things over to our FPL presenters today. We are so happy they could be here with us, so let's give them a round of applause.
All right, good morning, everybody. How are you? All right, you guys are ready to have some fun, learn some stuff? All right. All right, I'm Melanie Roger. I'm a chemical engineer at Florida Power and Light. Who here knows what Florida Power and Light is? Yeah, we're the power company. Yeah, good job. Yeah, we're the power company. We give you your safe and reliable power, right? Your electric that goes to fuel all your fun little iPads and iPods and all your gadgets and gadgets. So here, we wanted to, kind of bring what we do to what you do, and teach you a little bit about how do you build a generator. How many people here think building a generator is hard? Well, after this, you'll see how really, really easy it is. And what's awesome about this is the same concepts that you learned today are the same exact concepts we use in our power plants to fuel, to provide electricity to you guys. We just do it on a very large scale. So what you're going to do, you're going to do it on a small scale. We just do it on a very, very large scale. So, so without further ado, I'm going to just run through the presentation. What we're going to do, we're going to teach you the fundamentals first. It's going to be me and Andrew over here. Andrew, he just found out he's going to be a daddy. So, round of applause.
Last year we'll see Andrew.
So we're going to go through the concepts, and some of the concepts might seem a little, little high level, but we're going to bring it down and make it really simple for everybody to understand. And then at the end, by the time you leave here, you'll be making your own little generators. And the concepts you learn here are the basic ones. What we want to do is challenge every one of y'all to take what you learned and make it better. We've seen so many awesome generators built from the elementary, middle, and high school. We've been doing it about three or 4 years now. Yeah. And it just gets better and better and better and better every year. We'll teach you the basics. When you come into competition, don't replicate what we're showing you here. Think outside the box. We're going to give you a generator in a box. Think outside the box, make it bigger, better, and more fabulous. All right, so like I said, we're going to teach you the basic theory of electric generators, how you make one of those. We're going to go over the competition and scoring. When is the competition here for Broward?
April 16th.
April 16th?
Yes.
Okay, elementary, middle, and high?
All of it.
Okay. So you have between now and April 16th to come up with something fabulous. Okay. We're gonna tell you how to build a generator. We're gonna give you the basic instructions, and like I said, take it and run with it. We're gonna do a demonstration of a wind generator. So for elementary school, it's about turning. We're gonna talk about what a rotor is, but it's about turning your rotor, your magnets with a power drill. That'll be done by an adult. Middle school is all about wind, because another thing with the FPL, we provide electricity through many different means. Very, very clean energy. We have combined cycle plants using natural gas. We have wind turbines, largest wind fleet in, I believe, the world. And we also use solar. So you guys get to, when we're in middle school, get to build your own little wind generator. And for those in high school, you get to use water, so hydro, right? Okay, so basic theory of electric generators. So how does a generator work, right? So it's a machine designed to convert mechanical energy into electrical energy. And it's based on a principle called electromagnetic induction from a guy named Michael Faraday. Anybody ever heard of him? All right. Good job. Good job. What do you know about him? Pop quiz.
Yes?
Well,
He was always an astrologist. Was he? No? What?
all right, I won't put y'all on the spot.
Oh, I can do it.
All right, so we'll go into it, but basically, he discovered electromagnetic induction, and he found out that hey, all you need to create electricity is like three simple things, right? And if you get these three simple concepts, you can build your own generator at home. A magnetic field, and who can tell me what will create a magnetic field? Magnets, you got that right. Current carrying conductor, right? So, right? Wire, right? And basically motion between the two, right? Because when you think about it, wire is based of, what's the elementary building block of anything?
Copper.
Well, it's made up of atoms. There you go. Atoms. So there's billions and billions of atoms, and an atom is made up of what? Exactly. Protons, neutrons, and electrons. And basically, those little electrons, right, as a magnetic field crosses it and excites it, those little electrons will go crazy. And a wonderful thing about a current carrying conductor is the electrons will flow through the conductor, right? And hence, you're inducing a current, right? Which is proportional to a voltage, but it's when you think about there's something called Ohm's law, right? You know it? What is it?
It's V equals I.
Yes, which is voltage equals current times resistance. So basically, if we can reduce the resistance, right, we can increase our voltage. All right. All right. So magnets, like what we said, right? Magnets. It's all about material. It's a material object that produces a magnetic field. So magnets have a south pole and a north pole, and like poles. It says it on the board. Like poles. Yeah. Repel each other. Opposite poles attract each other. Right? You're going to need to know that because you're going to need to know what your north pole and what your south pole is. It's better if you get a compass because it kind of tells you, where your north and south pole are. Or you can just take two magnets and, try to figure it out, right? And the magnetic fields are strongest near the poles, right? This is very important. Your magnets, they can be polarized through the thickness or through the length. So when you're testing it, you got to see, is it repelling on the ends or is it repelling on the sides? This is going to be another very important concept when you're trying to build your generator, right? All right. So you got to figure out what kind of magnets you have. And we've seen both in this type of competition, and people get tripped up because they're like, oh, they try building it and they realize it's magnetized through the wrong way. Okay, so Faraday, we kind of talked about him. So his whole thing, don't get scared by the formula. But this basic thing is like, hey, electromagnetic induction, you have a magnetic field, you have a current conductor motion between the two, you will get a voltage. One of the ways that you can increase your voltage, and you need to know this because when you're building your generator, is increase the coils. So you're going to be coiling your wire, right? Coiling it in itself induces a voltage, and then of course coiling it around the magnetic field induces the voltage. So the tighter you make the coils, and the more coils you make. Of course, you're limited to 500 feet. You know, because when we designed this competition, we wanted to make sure it was safe, so we didn't zap anybody. So we limited the amount of wire, the footage of the wire, and the amount of the type of magnets you can use in the amount of magnets. And we can tell, based on the inductance, how much wire you have, so don't go over 500 feet or you'll be eliminated. It can be dangerous, it can be dangerous, and it'll be cheating. So. Another thing is to increase the speed of rotation. So how do you make things go faster? You reduce what? Friction. Yes. So there are a lot of cool ways to reduce friction using ball bearings, or we've seen some very, very low friction type devices made, which are very impressed us. So try to figure out ways to reduce the friction. Lighter magnets, like I said, we specify the type of magnets you use, so not much leeway there. And better ways, like if you're doing a wind, better ways to catch the wind, to spin the rotor. If you're doing a water, same thing. If it's hydro, same thing. And then if you're elementary and you're trying to spin it with a drill, how do you make it faster? How do you reduce that friction? And then increasing the magnetic flux. Here, like I said, you're kind of limited because everyone gets maximum. You can't use over 500 feet of wire, and you can't use over the specified magnet. But basically, how do you increase your magnetic flux? Use stronger magnet. Or ensure, what you can do is ensure the wire is as close to the magnetic fields as possible. So, that little gap between the magnet and the wire, the coiled wire, reduce that as much as possible. That you do have control over.
All right, good morning, everyone. One of the reasons, I guess, the main reason why we're having this workshop is today is kind of to educate you guys on how to build your generator so that when we come to the competition in April, we will all be ready to go. We don't have to call anybody to try to come back and fix your generator. So, starting with the competition rules, these are the rules that we set out for this year. Team entry. A minimum of 2, a maximum of 4 people can be per team, and a maximum of 2 teams per school. Now, the only exception to that is when you have a school that has a middle school, elementary school, and high school. Then there's 2 teams for each grade. Good? When it comes to the design, the construction of the generator and construct the generator and measure the highest voltage output. So basically what we're going to do is for the elementary school, we'll have them use a drill. We have when we start doing the actual hands-on, we'll show you guys the drill. The middle school will use the vacuum, it's like a wind that we'll use to see if we can generate some voltage. And in the high school, we're going to use water. Communications. Team will be interviewed by judges, so you will have both a written actual questions that you will answer on the day of the competition, and also we'll bring you to a room where you'll be interviewed by a couple of judges who will ask you to make sure that you truly understand the rules of overall. The teams will submit an abstract and a technical drawing. This only applies to the middle school and high school, not elementary schools.
Does elementary have to turn in anything other than the actual generator?
Just the generator.
No pictures, nothing else?
No pictures.
Okay.
Okay. So, for the guidelines, one of the things that we see is often when they built it, we're asking for maximum dimensions of 30 centimeters by 30 centimeters by 30 centimeters. This also will be online for you guys to download as well. No batteries or external voltage source will be used. One of the things that we've seen in a couple of years is that we'll see a generator, but then it will have some spoons or something aesthetic that will make it past the actual maximum dimensions. We want to make sure that we clearly specify for this competition, we want to stay within the limits. No generator kits are allowed. All items will be hand assembled. Generator must be able to run continuously for 30 seconds. So when it comes to materials that are acceptable are wood, cardboard, plastic, etc. can be used for the base of the generator. Long nails, screws, pencils, etc. can be used for the rotor. So you guys will see this when we start practicing today, where you can use like a pencil or a long bolt as your rotor. Thank you. So for the material list, this is what we are asking for the materials. 500 feet of maximum of number 28 AWG magnetic wire. You can find this online on Amazon. I know today we guys are providing you with the actual magnetic wire.
One thing about the magnetic wire, that it's insulated, to keep it safe. So when you go to connect it, the terminals, you got to strip the ends, the insulation off the ends.
Go ahead.
Were there any coordinators here that were not able to download the files that came through the CAB message that has PowerPoint, that has the rules?
That was the Palm Beach one?
It's a South Florida Alliance.
So the survival guide?
Right.
Okay.
But there was also a special email that came from FPNL that came with the rules.
Oh, I didn't,
No, I didn't.
it's posted on the website. I didn't blast out the email. It had a lot of attachments, so we just posted the PowerPoint on
I
the
think it was one
website.
of Eric's email. Did you?
When I sent out the invite, the PowerPoint was attached.
Oh, you
I can resend it if necessary. When I get back, or I can literally do it while I'm sitting here, I'll send it back.
Yeah, it's on the website. It's posted for download.
So for the magnets, elementary and middle school must use option A and B. So basically option A and B is just.
So
Go ahead, Chris.
you are allowing neodymium this year? Because in previous years
We
you,
don't usually
Oh, here? Yeah, I know
Yeah.
different districts.
Yeah,
Okay.
because of the size and the hazard in schools, we'd rather not have that.
Okay.
Okay.
So it'll just be.
So we'll
So for
provide you
Broward
with those,
County-
and those are cheaper too.
We're gonna use these. Okay.
The A version you're talking about?
The A version. Oh. Alright. These are strong magnets. Handle very carefully and avoid pinching because as you can see,
Yeah,
it's,
and they are fragile, so don't drop them on the floor, they will break.
okay? Alright, okay. Building instructions, is that it? And we go.
Okay, in this section, we'll talk about the more practical aspects of building a generator. A lot of these things I'm talking about right now, we're actually going to see them in practice, over the next hour as you all build a little generator in this workshop. First of all, the main parts of the generator, the rotating parts of the generator are called the rotor. Usually we use a nail, a screw, a metal rod. Anything that's long and cylindrical can work as a rotor. We always use strong permanent magnets and we mount them on the rotor. And the stationary parts of the generator are called the stator. And remember, we do have a little bit of a test along with the building of the generator. As a little hint, remembering what the rotor is and the stator is pretty important.
Stay on this side so that way everybody can see it.
Sure. Okay. over here I have a model, I have a diagram of a generator. And this is very similar to the generator that we're going to be showing a demonstration of today. The stationary parts of the generator were made out of wood, or can be made out of wood, cardboard, metal, plastic, whatever. Over here we have wire. I don't know, can we turn off the lights at the front so you see this a little bit better? Okay, so we have wire running around the edge of the stator. Good. You can see we have the rotor, which is like a long screw going through the stator, and we have magnets mounted on the rotor. Now to explain how this works, I'm going to talk about Fleming's right-hand rule. But before I do that, in this diagram, this is the same thing as this. This is just showing a cross-section of it. So if you cut away the front of the generator, you look straight down it. You see the magnet, North Pole and South Pole. You have the rotor in the middle, and you have the coils of wire on both sides. In electrical engineering, whenever we want to draw a wire going straight into or out of the paper, these are the symbols that we use. So if the current is going into the paper, we use a circle with a little cross inside it. Think of it like an arrow. If an arrow is going away from you, the back of the arrow looks like a cross, right? So that's why we use this symbol for a wire going straight into the paper with the current going into the paper. And if the current is coming out of the paper towards us, we use a circle with a little dot in it. It's kind of like an arrow coming towards you. The front of the arrow is just like a little point. So now for Fleming's right-hand rule, we can use this to tell us the direction that the current is going to be in once it's generated. The thumb represents motion, the direction that the magnetic field is moving. The first finger represents a magnetic field, and I'm going to be making strange symbols at you all here, nobody take offense. And the third finger represents current. So let's do it on this side of for the wire on the right of the magnet. Let's look at what direction the current is going to be. So if the rotor is spinning anti-clockwise, that means the North Pole is going up, South Pole is going down. So my motion is up. The magnetic field always goes out of the North Pole. So my field is to the right. And you can do it along with me. Because we've had lots of groups make mistakes with this. And I'm going to explain in the later slides how you can mess up your generator if you don't understand this properly. But motion is up, magnetic field to the right. That means that my current is going to be going into the paper. So if we do it in the three-dimensional drawing, if my North Pole is going up, magnetic field is going to the right, my current will be going into the paper that way, with that red arrow there. On the other side, if I look at the coils of wire on the left side, now my motion is going down, and it gets harder to do it, but my motion is going down. My magnetic field always goes into the South Pole. And that means that the current is coming out of the paper. Does everybody see that? And the key thing here is that on one side of the generator you have the current going that way, on the other side the current is coming this way. So the current goes around and around in a circle, it gets stronger and stronger. If you can somehow do this wrong, and I'll show you in later slides how you can do it wrong, the current will cancel each other out. The current will cancel itself out. So it's very important that you have the current going into the paper on one side, out of the paper on the other side, and that way it just adds up. Sorry, we had a question back there?
Oh, no, I was just verifying. So your field and your motion could be like an X and Y, and then your middle finger would be the Z going in the other direction.
That's a nice way to say it, yeah. One of the points of Fleming's right-hand rule that I think you're pointing out is that the motion, the magnetic field, and the current are in 3 different dimensions. Yeah. And as we start to wind up our generator, that's one common mistake that we always have. You'll notice that if the magnet is spinning this way, you have to wrap the wire this way. You know, if the magnet is spinning this way and you try to wrap the wire in the same dimension, it'll violate Fleming's right-hand rule and we won't get any current generated. Oh, thanks. Now this is an example of what not to do. In this case, and I have to say that all of these examples here is things that we've actually seen from the competition. So you all have an advantage over the people that did it the first couple years. We couldn't point this out to them. Okay, in this case, the poles don't point outwards. When Melanie spoke about the theory, she mentioned that you need a changing magnetic field. Can you go back one slide? In this case, when the poles are pointing outwards, initially this wire is seeing a north pole. Then as the magnet spins, it sees a south pole, then a north pole, then a south pole. So it sees a changing magnetic field. Next slide. In this case, this wire is seeing both the north and south pole. Even as it spins, it keeps on seeing the north and south pole. The magnetic field that it's seeing really isn't changing. So that violates one of the 3 basic things you need for a generator to work. And as I mentioned before, in this case, they wrap the wire this way. So the magnet is spinning this way. The wire is also spinning this way in the same dimension. That violates Fleming's right-hand rule. You're not going to get any voltage generated there. And in the last example, that one also violates Fleming's right-hand rule. We're going to walk through Fleming's right-hand rule there, and we're going to show why the currents cancel each other out. But instead of me doing it, can I get a volunteer? Does anybody think they understand Fleming's right-hand rule? Okay, I have a volunteer there. Want to come on up? Let's start with, and I'm going to need you to stand up right in front of it, like right here. A little bit more towards me. Yes, that way your shadow is in there. Okay, so let's start with the coil of wire on the right of the magnets. Can you show me using your thumb which direction the motion is going? So if you stick your hand out, which direction is the motion? Let's do it for, I need something to point with. So over here, the motion is going up, right? Yeah, let's stick your hand out. No, keep it up. Which direction is the magnetic field? Yeah. You know what? Let me get you to. Alright, so everybody sees that motion is up, magnetic field to the left. So which direction is my current going to be going? Show me with your finger. No, you had it just then. Okay, there you go. So on the right side of the magnets, the current is coming out of the paper. No, wait, hold on a second. All the way. Can't bend it. Yeah, I'm sorry, yeah, so the current should be going into the paper. Yeah, no, I was just testing you out. Let's do the same thing on the left side of the magnets. So my motion is going down. My magnetic field, is it going to the left or to the right? Yes, it's going to the right. So, okay. So my current, is it going into or out of the paper? Show me with your finger. So tuck these in. I have it down to the right. And this finger is going out. Does everybody see that? Motion down, magnetic field to the right, and current coming out of the paper. Everybody see that? Thank you very much. The point of doing all of that is that just to show that if you should construct your generator wrong, you have the current going on the same direction on both sides. That means that the current is going to cancel itself out, and the generator will produce no voltage, no current. We have had cases where this has happened, so.
It's also only seeing the south pole, right?
Exactly, yeah. And that's one of the key takeaways here. One side of the generator has to see a south pole, another side has to see a north pole. So this is all what not to do. Another key thing to remember, Melanie pointed out that you have two types of bar magnets out there. You can have the kind magnetized to the thickness and the kind magnetized to the length. We always want our poles to be pointing outwards. And for the most part, I'm showing you this kind of design. I don't know what kind of magnets you have. I haven't had a chance to inspect them. If you have that kind, then your generator is going to look a little bit different. So the first thing we're going to do when we get these magnets, we're going to hold them together lengthways, we're going to flip them over the other way. We're going to try and figure out what kind of magnet we have. And then as we start constructing this thing, we're going to make sure it's pointing, the poles are pointing outwards.
Does the rotor have to turn anti-clockwise?
No, it can turn either way, yeah. Alrighty? Okay, now this is a harder design. We actually give you 4 magnets each, and you can decide how you want to configure your magnets. In the design at the top, we call that a 2-pole generator, because a generator really just sees one north pole, one south pole, you know. And that's a simpler design. Some people may decide to go with a more complex design. All of the generators that we have at Florida Power and Light have multiple poles, have more than 2 poles. In the second one, I'm showing a 4-pole generator. So we can see that we have a north pole. We have 2 north poles sticking out, one at the top, one at the bottom, and 2 south poles on either end. We call this a 4-pole generator because it has 4 poles that are exposed. And the whole point of a 4-pole generator, you have a question?
Go ahead, Alan. Go ahead and finish your thought, Alan.
Okay. Now the advantage of a 4-pole generator is that when Melanie gave us our theory, she gave us Faraday's equation. Part of what gives you a higher voltage is having a higher rate of change of magnetic field. With the 2-pole generator, as you spin it 360 degrees, one side of the generator will see a north pole, then a south pole, then a north pole again. With a 4-pole generator, it goes north, south, north, south, north. The magnetic field changes quicker. It's oscillating between north and south quicker. You have a higher rate of change of magnetic field, you get a higher voltage. But in the last design, I'm showing you what not to do again. If you go with a 4-pole generator, it's very important that you go north.
Before we go on any further, for the kids, if you want to test the ideas of having more than 4 magnets, that's great. But when it comes to the rules for the competition, you're only allowed 4 magnets maximum.
So we can't cut
So
them in half
you-
and use the same 4 magnets, but as 8 pieces.
Oh, you're not allowed to cut them anymore?
There was the idea of that, but with Palm Beach County and Broward County coming up with what we thought would be fair. It's 4 magnets that we give you, and they have to stay intact. That's just to make the validity of it, and you know, the even playing field is not changing too many variables.
But you can build a 4-pole generator with 4
Yes.
magnets. Yeah. But okay, so what I was saying now is that you want to make sure that you're going north pole, south pole, north pole, south pole. In this case, you can see they have north poles next to each other and south poles next to each other. So as the generator is spinning, you may go north, north, south, south, and then back to north. If the magnetic field is changing from a north pole to a north pole, the magnetic field really isn't changing. If the magnetic field is not changing, you're not going to have any voltage. So in this case, that's a poor design, and you have a very low voltage generator. Okay, this is another example of what not to do. And the main takeaway here is, and I showed this with eight magnets, but you can do it with, no, actually that's 1, 2, 3, 4 magnets. That's 4 magnets. Okay, the main takeaway here is that this violated Fleming's right-hand rule again. They wired up the stator the same way you wrap a stator. They wrap the wire the same way you wrap it for a 2-pole generator, and that's a problem because both sides of the coil end up seeing the same polarity. Both sides in this case are seeing a south pole. You end up with the current in the same direction, and it cancels out. So this is an example of what not to do. If you go with a 4-pole generator, then now you need 2 separate coils, and you have to make sure that each coil goes between a north pole and a south pole, a north pole and a south pole. And then later on, when you wired up the 2 separate coils, you can connect them together. You have to be very careful how you connect them together. If you connect them together properly, they will add, and you'll get double the voltage. If you connect them together the wrong way, they subtract and you get 0 voltage. That's why it's better to wire it up completely separately, 2 separate things, and then you connect them afterwards. Next slide. These are just some examples of generators that we built. That one we built out of wood. This one we built out of cardboard. This is very similar to the one we're about to build in this workshop right now. And this one was out of an old peanut jar. I should also mention that once we're finished speaking, you can come up, you can look at some of the generators that were built by students in past years and past competitions. I think they did a great job. A lot of these generators that they built are better than the ones that we built. Next slide. This is an example of a real generator at FPL. Melanie, is that you?
No,
No, that was Wilma.
Oh, that's Billman. That's somebody who used to work with us. This is just to give you an idea of, we're building generators this size in this competition. That's what they really look like in real life, but it's really the same thing. Our generators are bigger, they have more bells and whistles, but if you know how that works, you know how that works. Okay, now this is the actual exercise that we'll be doing here today, but before we do that, can we turn the lights back on? Before we do that, I'm going to have Gibbons come up here and give you a little demonstration of a wind generator and also to show you the equipment that we use for the elementary and middle school.
Good morning, everyone. I'm Gibbons. So when we're going to be testing your generators and when you're testing them at home, the most important thing, first of all, is safety. So you want to have safety goggles, work gloves, because we have had cases where we were testing a generator and parts started flying all over the place and attacking people, so you don't want that to happen, but if it does, you have to be prepared and have safety glasses so you don't get anything in your eye. But make sure you build them strong and sturdy so that doesn't happen. So safety, you will clamp the generator down to the table so that they don't move around. So here's an example of the generator. The base is built out of wood. We have our stator, it's a wooden screw, magnets attached to it. I'm sorry, the rotor is a metal screw. The stator is the wood with the wires wrapped around it. The magnets are attached. And depending on whether you're elementary school, middle school, or high school, is what you're going to have to attach to your rotor. So in the case of elementary school, you just have your rotor sticking out, and we will attach this cordless drill to it. So we attach our drill to the end of the rotor, and we spin it for 30 seconds and measure your voltage with this device. It's a voltmeter. It'll tell you what voltage you're getting out. And for middle school is the wind competition. So you need to attach something to your rotor that's basically going to grab the wind and be able to spin your rotor. So I can give you a demonstration of how that works.
Now, you're not gonna be able to see it from back there, but we actually do have a little LED back here that will be turning, flashing, blinking on and off as the generator generates voltage.
Alright, so we use this vacuum cleaner, and you guys probably know vacuum sucks, but if we just attach our hose to the backside, we get the air coming out, and that's gonna blow our rotor. And you guys can't see it, but the light is blinking, showing that we are getting electricity. Alright, so
During the workshop, you can actually come up, you can test it for yourself, you can see the light blinking on and off. During the actual competition, you'll be holding the vacuum cleaner yourself. You'll be pouring the water yourself, which gets a little messy.
So, high school, you get 1 gallon of water, you get a funnel, and you have to build your rotor to have something that's going to catch the water. And basically, you just pour until you run out of water and get the voltage out of that. So that's pretty much it as far as our demonstration. Your generators are going to be pretty much the same as this, have the same concept, but wanted to look a little different, use different materials. Creativity and originality are part of your score, so